All right, folks. Picking up where we left off yesterday with this terminology, we have this figure here. It's a hexagon, right? 6 sides. I've shown you one central angle. There's 6 of them. I've shown you one apothem. There's 6 of them. I've shown you 2 radii. How many radii are there going to be? 6 of them. That is all of the vocabulary we talked about yesterday placed into one image. Okay, there's another image below this, and this is the one. This is kind of the picture that I usually use. I think that's a terrible picture, but let's look at this one here real quick. And I wrote it this way. I drew it this way so that there wasn't a whole lot of overlap with words and all that kind of stuff. When you do these problems, that's going to be the picture that you need. Okay? You're going to need one radius. You're going to need your apothem. You're going to need this angle right here where my cursor is, which is what compared to the central angle? It's half the central angle. Okay? And every polygon that we come across, no matter how many sides it has, you can end up drawing it to where you can focus on really that image right there. So if I have a 30-sided polygon, okay, let's just go to GeoGebra real quick. Well, we'll just use this 12-sided, okay? If I look at this 12-sided and I zoom in far enough, can you see kind of this image where this segment, a flat bottom segment, and then this segment going off where this would be the apothem coming through here, and then we could have this radius coming through here. Does that make sense? So every single regular polygon, you can zoom in, and you're going to have this kind of image. Okay. Now, the greater the number of sides, these things are going to be either, these kind of second and third sides are going to be maybe more flat. Okay. But it doesn't matter. We need this image here. Okay. Because those are going to be the things that allow us to come up with our area of this shape. Okay, so we're going to need that triangle. Now, what I'd like to do is work through here a procedure that allows us to find this formula. Okay, I think if you were in like a lower level geometry, I'd just give you the formula and say we're going to use it. It is what it is. But I think here maybe we can do some work to actually find why that formula works. Okay, so the area of a regular polygon is equal to half the product of the apothem and the perimeter. So 1/2 AP, where A represents the apothem and P represents the perimeter. And I'll give you a minute to write this down because I think this is important here to make sure we have that, or we've made note of that as we move forward. All right. So we know that so that's going to be the center of our regular polygon. We're going to have that radius and that radius. Okay, so what kind of if those are radii of the polygon, but they're also radii of that circle that is circumscribed around it. So there's a circle that goes around here. What is that? What is that? If those are radii of that circle, what does that tell me about their lengths? They're the same, right? Okay. If I draw this thing down right here, okay, which is the apothem, okay, that's the apothem. Would you guys agree that the area of that triangle, is going to be 1/2 B times H? You guys agree with that? Okay. Now, the base and the altitude, or H, are that and that. Okay. So what I want to do here is I'm going to relabel some stuff. 1/2 B I'm just going to call this here S for side. Okay, side length. So that's what I'm going to say for B. And H is my apothem, so I'm going to call it A. Is that all right, everybody? Okay. Now, if that's the area of one of these triangles, okay, what would be the area of the entire figure? It'd be 6 times it, okay? And that would give me a formula for just a hexagon. And then I have to go through the same process when I go to a pentagon. But the 6 would change to a 5, right? If I want to go to a square, the 6 would change to a 4. If I wanted to go to an octagon, for example, the 6 would change to an 8, right? But it would be the same exact procedure. So let's say that even though the picture I'm using here is a hexagon, let's just say it was an n-gon. Okay? So if I have 6 sides, I can make 6 congruent triangles in there, right? If I have 7 sides, I can make 7 congruent triangles. If I had 8 sides, it'd be 8 congruent triangles. Everyone on board with that? Okay. So instead of multiplying it by 6, let's multiply it by n. So I had 1/2 S times A times n, and that would be the area of the regular polygon. Okay. Now that's not 1/2 AP, is it? It is. We do have the 1/2 A. Okay. But then the other stuff that we have here is S times N. And remember what S was? S was the length of a side, right? And N is in how many sides you had. What does that equate to? The perimeter. Okay? S times N is basically S plus S plus S plus S n times, which is exactly how you find perimeter. Okay? So we make the substitution, then that S times N is capital P for perimeter, and that's our area formula. Okay? Now, real quick, here's my question. What shape did we get that area formula from? A rectangle, right? So do you see, now it might be far-fetched, but do you see that because of the area of a rectangle, we can generate the area of a regular polygon? And what that does for us, guys, is that allows us to have one formula. Okay, so let's see if we can demonstrate this real quick. So we'll make a slider here that goes from 3, because 3 sides is the smallest polygon we can have, right? Okay. I'm going to go make it go up to 50, big increments of 1. And I'm going to now say that I want to make a polygon, a regular polygon, but I want my number of sides to be based off of A here. And right there you see that it made a polygon of 3. So now this is a regular, so if it's a regular triangle, that means it is a equilateral or equiangular triangle, right? So an equilateral, equiangular triangle, that is a regular triangle. So regular polygon. If you wanted to use 1/2 AP to find this area, you could. Okay, 1/2 the apothem times perimeter. There's a square. Square is S times S, right? But I could also use this as my apothem, take 1/2 of its product with the perimeter, and I got another formula for finding the area of a square. Pentagon, 1/2 A times P. Hexagon, 1/2 A times P. Heptagon, octagon, nonagon, decagon, a neagon, dodecagon, triskydecagon. Okay, we got all of these different shapes. We can find the area of all of these. Okay, with how many formulas? 1. Okay, Is that much better than having an individual formula for all of 50 of these? And when I say 50, that's a very, very small amount because this can ultimately go out to infinity, right? So I wouldn't want to memorize or have to recall each of those different individual formulas. 1/2 AP takes care of all of them, okay, which is a really, really nice thing, okay? So there's kind of three versions, I believe, of the problems that you're going to see, and it's all predicated off of what they give you. They can give you the perimeter, they can give you the side length, or they can give you the apothem, okay? And those are going to be the three things that they can give you. They'll only give you usually one of those, and through our knowledge of trig, we can come up with the others to fill into that formula, okay? So in this case, they just give me a side length, okay? So this is a hexagon, try to find the area of this, and you're going to see patterns because, you know, every hexagon is going to have some similar features that every other hexagon has. And you might say, okay, well, I've done a hexagon many a times. I can recognize a pattern that can help me find some of these values a little bit quicker. I'm going to approach them all as new problems, just so we get the habit of that. I don't want to show shortcuts before we get the real hang of what's going on. But I'm going to fill in my formula, 1/2 AP. Okay? And I'm going to write down the things I know. Do I know directly from this image what the apothem is? Nope. Do I know what the perimeter is? They tell me a side's 15, but can I find the perimeter pretty quick, though? So 15 times 6 gives me, what, 90? So I fill in the things that I know or the things that I can grab and figure out real fast. And then it's a matter of now using my trigonometry to help out here. Okay? We need to figure out the apothem. The apothem is that segment right there. That red segment that is attached to this isosceles triangle. And if it's perpendicular down here, we talked about this yesterday, if it's perpendicular down here, and that's by the definition of apothem it has to be, then it is also an angle bisector up here. Does that make sense? Okay. Do you guys remember finding that angle yesterday, how we found that central angle? Central angle is always, okay, good. So 360 divided by n, okay? Now, that's great, that's fine, but ultimately, we don't want just that central angle. We want this part of that central angle, okay? So how big is that? Because, and that's why I talked about this angle, this apothem being an angle bisector. If that's 60, or 360 divided by n, isn't this right here going to be 360 divided by n, and then divided by 2? Does that make sense? And if I divide this by 2, like that, algebraically, that tells me to take that reciprocal, multiply by the numerator, and I get 360 over 2n. Okay, and that is, I'm going to write here that it's half the central angle. And that's what we want every single problem. Okay, we're going to want this angle right here because it's it's an angle of a right triangle. And what that's going to allow us to do is either use special right triangles or SOHCAHTOA to find the apothem. So, if I take 360, so n here, n is 6, right? So if I go 360 divided by 2n, which would be 12, what's that give me here? 30 degrees. So that angle is 30 degrees, which is nice, okay, because now it's a 30, 60, 90 triangle, correct? What is this distance right here? What is this distance? 15. So just take a stab in the dark. What do you think this distance, the smaller distance is? Half of it, okay? And that, again, comes from the knowledge that if this was an isosceles triangle that we started with, and the apothem is perpendicular down here, the apothem bisects that side. So this is 15 over 2. Now, I leave it at 15 over 2 because some people are going to want to go 17.5, right? I'm going to leave it at 15 over 2 because I know when the triangle is 30, 60, 90 that they're going to ask me to leave it as an exact answer, and it's going to bulk at the 7.5 as a coefficient in any of my problems. Does that make sense? So if that's 15 over 2, that's the inside in a 30, 60, 90, right? What would this side here be? It's the n radical 3 side. So n is 15 over 2, and then I multiply it by radical 3. And now we have our apothem. So if I go 1/2 a, which is 15 radical 3 over 2, and then multiply that by 90, okay, what's 90 times 10? 900, right? What's 90 times 5? 450, right? What's 900 plus 450? 1350, right? So you get 1350 radical 3 all over 2 times 2 times 1, which is 4, right? Okay. Now, is 1350 divisible by 4? All right, it's divisible only by 2. Okay. So if I put 2 in there, it gives me 675 radical 3 all over 2. And this would be square units, and that's my exact answer. And hopefully, so what I always like to see is, just as I'm learning something new, is there a tool somewhere that can tell me or confirm to me that formula actually does work, and that area that I just presented here is legit, like it's not something that's just out in left field, okay? So, GeoGebra allows for this. I can create a segment with a given length. So I want this segment to be 15. And that's going to be my side length for this hexagon that I'm about to build. Okay, so they're calling that segment F. Okay, so what I'm going to do is I'm going to create a hexagon here, regular hexagon. Actually, I got to do it this way, Control Z. I'm going to go from there to there. So I'm going to say 6 sides, 6 vertices, and I've got that right there. Okay, so I just created this hexagon, and it has side lengths of 15. Is that okay with everybody? Which is the exact information that we started with our problem. We found our answer to be, was it 675 square root of 3 all over 2. I think I need a multiplication sign here. Okay. What we're seeing right here is the area that GeoGebra is able to calculate by basically taking a bunch of little small squares and seeing how many they can fit in there. Okay. If I type this in, hit enter, does it give me, so it's showing right here, does it give me the same thing that GeoGebra found? Does that make sense? So we've got two things, two procedures here that are being done differently, getting the same area. So that confirms to us that this formula is a legitimate formula, okay? This answer is better than this answer, okay? Because this answer, even if I go out to 15 decimal places, you don't see any repetition or anything like that, so this is rounded, okay? This one has absolutely no rounding. That kind of makes sense? Okay. Now, let's kind of talk about the figures real quick, and this might be something that you want to write down so that you have to reference in your homework. If we look at, and let's just do this in GeoGebra because I think it'd be a little bit easier to actually work through and see. If I find the center of this shape, so let's find the center there, and I'm going to go perpendicular from there to there. I'll come back, just trying to get this thing to show me the apothem. All right, so that's the apothem in that triangle, right? Okay, let's just see if this was built right. So it's always going to give me, as I continue through there, give me the apothem in one radius, right? Let's look at this angle right here. Let's figure out what that angle is. From there to there, 60 degrees. Okay? So when they give me a regular triangle, an equilateral triangle, when I break that and I find half that central angle, it creates that little triangle in there. Let me color that little triangle so I can talk about it a little bit easier. Okay, it gives me that pink triangle, purple triangle, and it produces a 60-degree angle in there, right? So when they give me a regular triangle to find the area of, and I want to use 1/2 AP, they're going to ask me in this case to do it with exact values because that purple triangle is a 30, 60, 90 now. Does that make sense? Okay. If they give me a four-sided figure, they give me a square, and they ask me to come up with the area using 1/2 AP. They're going to want it as an exact answer because that purple triangle now is a special right triangle. It's a 45, 45, 90, correct? If I go to a five-sided, can I use special right triangles now with that purple triangle? Do we have a 36, 54, 90 template for that type of triangle? We don't, right? So what takes the place? If I don't have a special right triangle, what takes the place of special right triangles when we are going through and finding distances? SOHCAHTOA, okay? So right now, I think maybe it might make sense to say, okay, if n is 3 or n is 4, okay, and n being the number of sides, you're probably going to use special right triangles, okay? When n is 5, you're not. When I go to n to be 6, do I use special right triangles? Special right triangles when n is 6, right? Now, let's just kind of think about what's going on here. What's happening as I get more and more sides? What is happening to that angle? Started at 60, 45, 36, 30. Decreasing, right? The more sides I get, the smaller that angle becomes. Okay? So, as we think about like the way that our authors write our textbooks, they want you to continually practice concepts that you've already learned. Okay? So they're going to give you a lot of triangles in this regular polygon section. They're going to give you a lot of squares. But the number one thing they give you is hexagons. Okay? Because we already have formulas for that one and that one, right? Now, it won't be uncommon to see them in this section, but we don't already have a formula for that. So this would be allow us to directly use 1/2 AP. Okay? Does that make sense, everybody? But everything else then, okay, all these other shapes you're going to use SOHCAHTOA. They like to give you octagons because that angle is a pretty nice, concise 23.5. That angle is not all that nice. Okay? That angle is not all that nice. Okay? If they give me an odd number of sides, that central angle gets pretty ugly. Is that okay? All right, so as we move on, doing a couple other examples, you're going to see a lot of questions that deal, like I said, with those three figures. But there's nothing wrong with a pentagon. Doing a pentagon, okay? So if I'm going to do a pentagon, I'm going to draw my apothem. I'm going to draw my radius. Okay. Now in this one, they are direct with telling you what your perimeter is, right? It says perimeter is 40 centimeters. So I got 1/2 my apothem times 40. Okay. So if they give me the side lengths or they give me the perimeter, then we have to work to find the apothem. If they give you the apothem, you'll have to work to find the perimeter. Okay. But the amount of work is about the same regardless of what part they give you. So if they give me the perimeter, what is each side length going to be? Each side length is going to be 8, right? What would this distance right here be? 4. Okay. Now if I want to find A, I need to know what kind of right triangle this is. So do you guys remember how we find that angle? 360 divided by 2n, right? So 2n in this case would be 10. So it gives me 36 degrees. That angle there is 36 degrees. What trigonometric ratio are you going to use to find A now? If I use this 36 degrees. I'm going to use SOHCAHTOA, but 4 is what compared to 36? Opposite. And A is adjacent. So should I use tangent? Tangent 36 is equal to opposite over adjacent. Okay, I'm going to cross multiply or multiply by both sides by this LCD. But what's going to happen, hopefully we remember the pattern. What happens when A is on the bottom over here? Okay, so first I'm going to multiply both sides by A, right? And they'll cancel that way. And then divide by tangent 36, so I get 4 divided by tangent 30. Is that what you meant? Okay. So the idea is that when my variable is the denominator there, really those two things I just highlighted switch spots, correct? Okay. So now I've got my apothem. Now, a lot of times you might not be asked this, but when we get to, maybe a college algebra trigonometry class, they might ask you to type your answer in as an exact answer. So right now I'm going to go 1/2. This is my apothem, 4 divided by tangent of 36, and my perimeter is 40. Okay. Even though this has got a word in it, I still treat it just like a nut. Tangent 36 is just a number. So I'm going to cancel that 4 and that 2. So I have 1 times 2 times 40, which is 80, divided then by tangent of 36. Okay. I like for us to be able to do that algebra, okay, because refining our algebra skills is always a priority no matter what math class we're in. Okay. So that is the exact answer. Okay. And once I have the exact answer, can I then type that into my calculator and get any level of precision that I want? My fear is that people do this because they know that the apothem is 4 divided by tangent of 36. Okay? So we know that our apothem is that length. And that they then take and say, okay, well, I gotta go 1/2 my apothem. Someone should say it's 5.51, and then multiply it by the perimeter of 40, and they get that. Okay? But in all actuality, if they would have just left it as 80 divided by tangent of 36, you see better precision here than what you had there, right? Does that make sense to everybody? Okay. Desmos does a good job of allowing you to kind of eliminate that. If you want to use intermediate values like this, you can label it A, and then come down here, and instead of putting 5.51 in, just put A in, and now you can see that those two numbers are out to that. Actually, as far as we need to go, they're going to be the same. So that's an option. Give that one a shot. Find the area of a regular hexagon with an apothem of 9. All right, so your apothem is 9, right? What is this angle right here? 30 degrees. Okay, so it's pattern based, right? Got a lot of hexagons. As we go through all the assignments that we do with this, you're gonna see that the hexagon is a very common shape for them to give us. So what side is that in regards to a 30, 60, 90? That's my n radical 3 side. So then n is going to be 9 divided by radical 3, right? Now you could choose to rationalize that now or later. I think because 9 and 3 work together well, I will rationalize it now. You'll get the same answer if you don't later on. Does that give you 3 radical 3? Okay. So that's n, which is this distance right here, correct? 3 radical 3. So what would this distance here be? 6 radical 3, right? My hope is that we realize that when we're going through a 1/2 AP, if we filled things in so far, we have our apothem to be 9. We just don't have the perimeter, right? So we need to find one side length. Okay, and now what do I do with that one side length? Multiply it by 6 in this case, so I get 36 radical 3. Okay, I could have, so I always double. I always get that distance and then double it to get this one and then multiply it by n. But if you want to multiply, so if you want to take that number right there, 3 radical 3, which is that side length of that triangle, and multiply it by 2n, so in this case multiply by 12, it will give you what you need here for your perimeter. Okay. Now, what numbers work? So my hopes are we realize that radical 3 doesn't work well with any of those values. But which two that I did not highlight work the best together? 36.5, right? Okay. So if I multiply 36 and 1/2, I get 18. So I get 9 times 18 radical 3. What's 10 times 18? 180, right? Now I go 9 times 18. That's 1 less 18 than what I did when I did 10, right? Okay. So what's that going to give me? 162. So you get 162 radical 3 units squared for that area. That is the one, that one. And let's see if I've got one that gives us a radius. Okay, this one is often difficult as well. Okay. Usually, if I give you the perimeter, or give you a side length, people are usually perfectly fine with those. The opossum is not bad. That's the one we just did. But here I give you a radius. Okay, here I give you a radius. And I say find the area of a regular polygon with 11 sides inscribed in a circle with a radius of 12. So when I say inscribed in a circle, which one is inside? Is the circle inside, or is the 11 gon inside? The 11 gon is inside. So when I draw this circle around here, see if this will work. When I draw that circle around there, okay, it says the circle has a radius of 12. So there's a lot of different places I can put the radius of the circle, but I'm going to put it right there. I'm going to say that's 12. Why would I do that? That's because then doesn't the polygon have a radius of 12? Does that make sense to everybody? Okay. So now, the reason I think these are the more difficult problems is because when I go area equals 1/2 AP, I don't know either of A or P. Okay. I know the radius, and that's it. Okay. So what we're going to do, we're going to still drop that line down. So it's perpendicular, so that's going to be that little triangle that we use. I need to figure out that angle. So remember, that angle is going to be 360 divided by 2n. In this case, it would be 22. So we're going to take 360 divided by 22. And here's where you got to start approximating things, because this gives me 16.36, and that 36 is repeating. Okay. If I didn't want to approximate, which I never do, but I don't want to get this far with you guys, that's 16.36 degrees. But I could keep it as 360 over 22 or 180 over 11 degrees. Does that make sense? I could actually use the fraction if I wanted to. Maybe we'll see what the degree of error that's created by rounding this. Okay, and see if it's a big deal. So that's that angle. Okay, I need to find A, or I need to find, I'll just call this down here, let's call it B, for lack of a better letter. I need to find those. Okay? And I know that this is 16.36 angle right there, and I know that my radius is 12. How can I find, let's just say A. How can I find A? What side is A in comparison to this green angle here? Say it again. That's going to be the adjacent. 12 is going to be 12 is the one that's across from the right angle. So 12's got to be the hypotenuse. So which trig ratio would you use for adjacent and hypotenuse? Cosine. So I'm going to say cosine of that 16.36, okay, is equal to adjacent divided by hypotenuse. So A over 12. So 12 cosine of 16.36 is equal to my apothem. Okay? Now, once you have your apothem, you have some strategies that could be used. Once I have my apothem and I calculate that on my computer or whatever, could I use the Pythagorean theorem to find B? Yes. But in finding B, then, I would have used a rounded value, right? A would have to be rounded, okay? Unless I'm creative with my calculator. So it's an option. It's not the best option, though, okay? Depending on the level of precision that the question is asking for, I would probably argue that everything we do in this class, that would be okay. It would work. But since we're in the mode of using SOHCAHTOA, can't I use B as opposite 12 as the hypotenuse and say that the sine of 16.36 is equal to opposite over hypotenuse and that gives me my B value. Okay. Now, what a lot of people will want to do, because B is not part of my formula, 1/2 AP. What a lot of people want to do is they want to take their calculator out right now and type in 12 sine 16.36 and hit enter. And then they'll get a number and say, okay, well, I'm going to take that number and I'm going to either shorten that number, round that number, or leave it alone, but then multiply it by 2 because they want to get a full side length of this polygon. But if I do that, that 16.36 rounding error just got compounded twice. It got amplified twice. Does that make sense? And then to get the perimeter, they're going to multiply it by 11. So now that rounding error of the 16.36 that was run through the sine function has now been amplified 22 times. Does that make sense? Do you see how many different levels of error can be created with this stuff? So my suggestion to you is to know that this B value is just that side right there. If I double it, it would look like this. 2 times 12 sine of 16.36 repeating. And that would be a side length. We say S for side length. Okay, and then if I multiply that by 11, so 11 times 2 times 12 sine of 16.36, that would be my perimeter. And 11 times 2, so 22 times 12, times 12, 264. 264 sine of 16.36 equals my perimeter. Or, let's just be thoughtful of this, 264 sine, if I left this angle as 360 over 22 as my perimeter, and it come up here and wrote that as 360 over 22, there'd be absolutely no rounding error in my problem. Does that make sense? Okay. And the reason I talk about the rounding error is because you might get in a homework problem and it says round to the nearest thousandths place. Okay. So round to 3 decimal places. Well, if you go through the problem and you round all your problem, even if you're cognizant of, they want 3 decimal places, so I'm going to round everything in mine to 4 or 5 decimal places, because there's so many different locations that rounding error can occur. That can culminate to being something that impacts the thousandths place, even though you thought you went far enough in your other calculations. Does that make sense? So if you can avoid it, which is always the best thing, avoid it. So going to our calc, and I strongly suggest you guys use Desmos. Okay, it's going to be the calculator that the end of course exam lets you use. So if we go. This is what I like to do. I like to go, my apothem, we just said when we wrote it out was, 12 cosine of 16.36. Well, so we'll do the rounding here first. So 16.36. And then we found what the perimeter to be, I can go 2 times 11 times 12, okay, or the 264 times then sine of 16.36. So if I go 1/2 A times P, there's my area. Now that's using this rounded value, right? Okay. If I would do this without the rounded value, okay, so let me cut this number. Paste it, and then we'll put 22 or 360 divided by 22 here. And that, can you see that the rounding error is pretty substantial by doing that. Okay, and that's what I've always feared in this with Math Excel. If I was giving you a textbook question, or if the end of course exam was multiple choice, we wouldn't probably be talking much about this. Okay, but the end of course exam is not multiple choice, and Math Excel is not paper and pencil to where I could read your answer and say, yeah, you're in the ballpark, you did everything right. Okay, you're going to type in 42 or 428.10, think you did everything right, and you did, but it says the feedback is that you're wrong because of rounding error, right? You get on the end of course exam and you type that in. It's going to tell you are a bad geometry student because you were bad at rounding, okay, or realizing that there was rounding, okay? Does that make sense to everybody? All right, and I've had people, it's very few over the last 12, 13 years. I've probably had maybe 5 or 6 people not get enough points to get the required 3 on that geometry test. Okay. If I go back to their scores, like the threshold was like 400 points. They got like 398 or 397. Okay, which equates to probably 1 question. And what would suck is to go back and look at their actual test, and maybe they missed a question because of rounding error, or maybe they missed a question because they put 4,5 and it should have been 4.5 as their answer. The computer counts it wrong. The state doesn't get into the nitty-gritty of looking at, okay, where are the typos at and that kind of stuff. They count it wrong and say you're bad at geometry because you couldn't type. Does that kind of make sense? So that's why I talk about these things, so it's always in the back of our mind. I know it's kind of boring to talk about, but it's always in the back of our mind when we're doing problems. Okay. On the ACT, if you did on the ACT, if you had rounding error of 428.10, but the only answer that was close to that was 428.18, you'd probably select the 428.18, right? Even though it's not the answer that you came up with. Okay, because the other ones are going to be far off enough that you're going to realize, oh, I've done it right. I just must have had rounding error in my problem. So multiple choice tests and the way that the end of course exam tests are developed, strategies of working through problems might be a little bit different.